Hello, everyone. What I'd like to do in this video is prove that big LP is complete for P between 1 and infinity. So I did little LP in the Introduction to Banach Spaces video. So this is a little more involved. Or it's not any harder, just requires a little more sophisticated tools. So one kind of trivial note, that's an easy homework. If we have a sequence, a finite sequence, in a normed vector space, then by an easy induction, we have the triangle inequality holds, not just for two elements, but for any number of elements. And if the infinite sum converges to something, then this is also true. Let's replace big N with infinity, and if this converges and big X. Okay. So a homework that I did assign in my AMAT 611 is, again, let's say X is a normed vector space. So suppose X satisfies the following. Very easy to prove, but it's ever so convenient and useful. So assume every Cauchy sequence has a convergent subsequence. So remember, completeness is that every Cauchy sequence is convergent. We're saying, let's relax this a little bit, and let's say we can pick a convergent subsequence from every Cauchy sequence. And by convergent, I mean it converges to something in big X. Then I claim that this is equivalent to completeness. So certainly the original sequence itself is a convergent subsequence if the original sequence converges. Completeness implies this is trivial. The easy but not necessarily trivial consequence is that this is enough to prove or to give us completeness. Okay, so now we can get to the following theorem. I'm just going to state it for a measurable subset of the real line. The same proof works for any measure space whatsoever. The details are literally identical. So I'm just going to prove this for P between 1 and infinity. P equals infinity is a homework. It's not a hard thing to prove using basic facts of L infinity. So that's a homework. Yeah, it's pretty straight, but relatively straightforward. Proof is completely different. Yeah. Actually, let me check if it's completely different. It's not, so I apologize. It's not completely different. It's a little bit different. But it's, yeah, I'll maybe outline how to do it. Yeah, I'll outline how to basically do it. Okay, so let me remind you what Cauchy means. So let's say Fn let's say this is Cauchy. So for any epsilon bigger than 0, there exists n where m bigger than n implies that there's just definition of Cauchy. This is less than epsilon. Okay. So let's set epsilon to be 2 to the minus j. Really anything summable in j works. 1 over j squared works. 1 over j to any power bigger than 1 works. But anyway. So I'm going to call this nj tilde because I'm going to let nj be something a little different. So I'm just picking an integer from here. Yeah, this is just the definition of Cauchy. That's it. Less than 2 to minus the j. Okay. All right, so I basically want to take these, and these are not necessarily increasing, so I want to just kind of make it increasing, and kind of do sort of the trivial thing. Start off with n1 tilde, let n1 be n1 tilde. And let's say nj for j bigger than 1 is the maximum of nj minus 1 and so why does this work and why do I want this? I'll explain in a second. Okay, so first of all, so nj is certainly bigger or equal to, sorry, it's not bigger or equal to, it's bigger than nj minus 1. Because nj is, yeah, so nj is bigger or equal to nj minus 1 plus 1. That's bigger than nj minus 1. So that's really, I don't care about this 1. I could stick anything positive here. I really just want this. This is bigger than nj minus 1. Okay. All right, so I'm going to use these to form a subsequence. So I do have a subsequence that I can form from these because it's increasing for all j. And also, nj is bigger or equal to nj tilde plus 1 is bigger than nj tilde. Okay. Okay, so what this means is, so the conclusion here is that nj is bigger than nj minus 1 is bigger than nj minus 1 tilde. So I'll put this in a blue box because this is key here. So in particular, what I'm going to do next, well, let me do something first. So this is not going to be immediate, but it's going to take a little bit of work. That's okay. So yeah. Well, so I'm going to claim that this is convergent in LPE. And as a it's part of the proof, and it's an unavoidable part of the proof. But it's cool that we can get this. This is convergent pointwise almost everywhere on to some measurable function f of x on E. That is an infinity symbol. Sorry about that. Okay, so why is this true? First of all, so let's say, use purple here. So actually, let me get rid of this. This is a lot of space here. Sorry. Let's say this is M, and let's say this is N. I don't care that M is bigger than N when I use the Cauchy property, but I basically have two integers M and N bigger than N tilde J minus 1. So I can use this here. Okay. So again, just remember I'm using M here, NJ, and N, NJ minus 1. Okay. The LP norm of the difference of those two functions, f n j and f n j minus 1, is less than 2 to the minus j plus 1, just from this here. Okay. So this is less than 2 to the minus j plus 1, and in particular, this here is convergent. Sorry. All right, so yeah, so sorry. I actually, well, this is fine. So I do nj plus 1, nj. So this is equal to j is going from 2 to infinity, fnj minus fnj minus 1. I just don't feel like erasing a whole bunch of stuff here, so I'm going to leave it as this and start from j equals 2 to infinity. fn0 is not defined, so don't want to work with that. Yeah, this is less than 2 minus j plus 1. So this is finite. Okay, so let's put this to excellent use, and we're going to actually use the Calc 2 principle that absolute convergence of complex numbers, or absolute convergence of I guess not Calc 2, but there's a principle that absolute convergence of complex numbers or absolute convergence implies conditional convergence for a sum. Okay, so let's see how we do that. So let's set HK, and you can call it whatever you want. H, any letter. Maybe I should do S for sum, whatever, doesn't matter. So let's say J equals 2 to K. Let me do this. J equals 1 to K. It's a little easier to just work with this. Sorry, I do not want norms. So I'll just take absolute value. So every element, every one of these is an LP. So that means it's finite almost everywhere. So this difference makes sense almost everywhere. It's this difference, for almost every X, this is a difference of two real numbers, two complex numbers. So there's no ambiguity here. Okay. And let's say H of X is this infinite sum right here, H of X. So by the monotone convergence theorem, let's look at this integral. So that made no sense. I want it to be exactly what I had before, just J equals 1 to infinity. So this is f n j plus 1 of X minus f n j of X. Okay. This initially, we don't know if this is infinity or not. The sum technically could be positive infinity for almost all X. We'll show that it's not, but even initially, if it is, that's okay. Regardless, the monotone convergence theorem from integration theory says that this is going to be the limit. Certainly, HK is monotone increasing trivially for almost every X. And you might be able to see where this is going. Okay, so this is equal to, just plop in the definition of HK just by definition, yeah, integrate this to the, well, yeah, so this is trivially by definition the, LP norm of HK, which we're just writing out what HK is. So this here, do it in green. This is HK of X, so it's just the LP. This is just the LP norm of HK of X. So I use the triangle inequality. This is less than or equal to this limit. K goes to infinity. So one kind of thing to note, so this is really the LP norm. Make these bigger. Of this absolute value. But I mean, I'm just taking two absolute values. So it's a little silly to keep the absolute value here. This is not incorrect. Let me draw these a little straighter. A bunch of stuff in my way that you can't see thanks to Zoom. Bear with me a second. Right. So yeah, taking the norm and the absolute value just puts two absolute values inside. So it's the same thing if we don't have an absolute value. Well, this member is less than 2 to the minus j plus, oops. So this is finite. Okay, so let's think about what we've proved. We have proven that this integral is finite. The integral of h of x to the p is finite. Sorry. Doesn't make any sense. Yeah, sorry about that. That was a little weird. So I'll just write that as a conclusion. This implies h of x is less than infinity for almost every x in E. Okay, that is super, super useful. Okay, so let's put this to good use. Okay, so what's the point of all this? Well, what this means, remember h of x is there we go. This is h of x. So absolute convergence implies conditional convergence for a sum of complex numbers. So that means this sum without the absolute values converges. And you should notice that this is a collapsing sum. Now, I'm being redundant here, but I'm saying, this for almost every x, this converges. Okay, so I'll remind you of really what that means. Okay, so what that means is so I claim this limit pointwise exists almost everywhere. Why? So this is going to be equal to this limit here. Oops, sorry. There's no way I'm going to fit it, so that's okay. I'll do it down here. Just bear with me a second. So it's f and j x. So actually, let's not even do limits here. So Right. So just trivially write out the terms here. You'll see that this is yeah, this collapses. This stuff cancels out here. So I'll just do a few of these. So let's say j equals 1, f and 2. I won't do of x, but I'll do it anyway. I mean, you should be able to see this, but in case you don't, was f and j equals 2, 3 of x. I'll do one more. Continue on. So in just this sum here, I still have an f minus fn1 of x, but that gets canceled out with this, so that's fine. So these cancel out. The 3's cancel out. So this is up to k equals 4. Sorry. So I really technically need a -1 here. Not a big deal. So this would be up to any, this would be k equals 3. Okay. In general, it goes up to f and k. And again, everything cancels in the sum except f and k and f minus f and 1, but that minus f and 1 is canceled by this. Okay. So what that means is just take limits. We're actually almost done. So literally take the limit right here. Take the limit as k goes to infinity. Plus this infinite sum. The definition as k goes to infinity, that is what the infinite sum is. Okay, well, this is something for almost every x. This is a complex number for almost every x. We said that this sum here converges for almost every x. Okay, so let's set f of x to be this limit here. Now it's an easy Fatou's lemma to show. This is really the hard part. Getting a convergent almost everywhere subsequence. Now the rest is just really Fatou's lemma. So I'll just rewrite the Cauchy definition. N such that n m bigger than n implies this is true. Remember, we start off with this Cauchy sequence. Epsilon. Okay, let's see. Okay, so let's see, 1 second. Okay, so actually, yeah, we're actually not going to even need to use yeah, so okay. So we actually don't even need the convergence subsequence little proposition at the beginning. I'll explain why in a second. So let's say n is bigger than n. So you want to look at this. Okay. So I'm going to use Fatou's lemma. So in particular, we have pointwise almost everywhere convergence of fnj or fnk, whatever, to f. So this is equal to and I'm just writing as a lim-inf. It really is a limit, but limit is lim-inf when you have convergent pointwise convergent, something pointwise converges. A lim-inf is a limit when the limit exists. So I can do j. Okay, so yeah, that's just pointwise convergence almost everywhere. Now use Fatou's lemma. And we're basically done. So Fatou's lemma says that this is less than or equal to the lim-inf. This integral here. F and j of x minus f n of x. Oops, I don't want to make that so big. It's such a pain in the ass to reduce in size. 1 second. Go. Okay, so this is this is less than or equal to epsilon, because we have a subsequence, so we can assume nj is bigger than big N. N is bigger than big N. So we have two things bigger than big N. I guess I probably should have switched it, but whatever. It's not a big deal. Okay, so these are both bigger than N. So and remember, this whole thing is literally the LP norm. I forgot to write it, but this is P of E. 1 second. Okay, and that takes care of the proof. So yeah, we really actually did not. It's a good homework, but we really didn't need this little proposition here. But anyway. Okay. Okay. So yeah, hopefully this helped and this was useful. Yeah, so yeah, nice example of a complete normed vector space. All right, so long. Take care. Bye bye.